Good morning. Um, Today's first lecture in this room is about virtualization. Thank you for coming. In the beginning, I thought I will have this talk with an empty room because it's day 4 and, well, we are all tired. So thank you again for coming. So what's about virtualization? I mean, virtualization is a technique you can use in computing for a broad field of applications. And of course, we are a hacker conference, so I'm trying to give you an introduction, like a sneak preview in the techniques of virtualization. So beginning, first question which arrives is, of course, what's virtualization? Virtualization is a framework or methodology of dividing the resources of a computer into multiple execution environments. Means you part the time, the bandwidth, everything which is inside a computer or can be accessed into small parts and give them away. Okay, what techniques are we using there? First, you probably think, yeah, well, I'm doing that the same at my home because my NAOS insert does concurrent time sharing, gives the hard disks to other processes, so that's quite fine. But virtualization is about running multiple operating systems at the same time. So, what can we do with it? Of course, the field of application for virtualization is quite broad. In a business meaning, first thing ever mentioned is, of course, server consolidation. You can put all of your 20 boxes into a few ones, and of course, this is good for business, this is good for administration. You can run your legacy applications. I mean, there are always some old, I don't know, MS-DOS programs, and you have that specific application built on it. And first, you need a hardware on top of you would like to run it. This is becoming more difficult anytime the PC is advancing. Wow, okay. So you put it into a box, and this box is an idealist machine, and you run this box on a real box. So that's about legacy applications. Of course, web browsing always gets more insecure. So what can you do with virtualization in this field? You simply put a box, meaning a virtualized hardware, a virtualized operating system, and a browser. And you can safely browse through the internet. If something happens, it happens inside the box. As soon as you're finished, reset it. So, for instance, firmware has recently announced the firmware player, I think. And there are pre-built images you can use exactly for this task. Just browse. Use Firefox in a virtual machine. don't be afraid of some viruses or worms or whatever. Of course, application mobility means virtualization gives us the power to move machines and, of course, the applications running on top of it from one machine to another. So that's quite cool, because if you want to maintain that server, and of course there's one critical application running on it, just move it to another server. Testing and debugging environments, always good to have a deep look inside the operating system while it is running. It's always a little bit complicated if you are working on the system. So it's a handy tool to get into a system without having the hassles of, well, something went wrong. Okay, I have to reboot my machine. You can make clean single application, single service environments. I mean, you don't have to set up your eierlegende Wollmilchsau. Okay, German native speakers would understand this. Basically an animal which gives you everything you want. You don't, I mean, it's good, but on the other hand, it's quite complicated to administer. So if you separate every reasonable service from each other, you have small machines which are quite clean to understand and easy to maintain. Nevertheless, the things businessmen always try to hammer in your brain what virtualization can make to you. It also gives you the freedom of choice in using multiple operating systems at once. Maybe you don't need this, but it's handy in case, okay, this program doesn't work on this platform, but I have another platform running, and well, I have 3 platforms running on my iBook, and it's okay. I can choose whatever application I want on whatever operating system I want. It's also a soft, I call it soft user migration path. So you migrate the user from one operating system to another. The point is, yeah, at one time you must switch over, and maybe it helps if you can run Linux for the first time in a box on top of your Windows machine and get a little bit used to it without having that hassle on it has to be the only operating system and stuff like that. Last but not least, virtualization is funny. I mean, at least for me. Okay. Next thing, what I want to talk about is a little bit of theory. Don't bother, it won't be long. I mean, at least 5 minutes. Afterwards, we are looking how we can achieve the techniques used in virtualization and what is used inside the machine monitor. And afterwards, we have some outlook into the future and what possible could happen in the future, in my opinion. But let's have a look at the theory. Some smart people have make their brain think a little bit more, and they found for a hardware platform, there are three main criteria. If this hardware platform is good for virtualization. So the first method is executing non-privileged instructions must have the same binary form in user mode or in system mode. This is a quite easy one. Most architectures fulfill it. Second, there must be a protection system or an address translation system to protect the real system and any other virtual machine from each other. Again, nothing very unusual in modern processor architecture. Third, there must be a way to automatically signal the virtual machine monitor. The virtual machine monitor, by the way, is that thing that runs on top of the hardware and that coordinates which machine now runs and has probably access to the hardware. So there must be a way to automatically signal the FIME, the virtual machine monitor, when a virtual machine attempts to execute a sensitive instruction. So what's a sensitive instruction? Basically everything which alters the state of the CPU, which alters the state of memory management, protection, and of course I/O. So instructions that attempt to change or reference the mode of the virtual machine or the state of the machine. Instructions that read and change sensitive registers and or memory locations. Storage protection system, memory system, and last but not least, I/O instructions. So, still does not look very sophisticated. We should do this on the Intel x86. So there are many people who have looked into it, and well, most processor architectures today have no problem with the three criteria mentioned before, but well, x86 is different. There are there are 17 privileged instructions that do not trap into user mode. In user mode, which means trap means if the processor executes these sensitive instructions, for instance, switch to another processor mode. Well, you should not do this in user mode, or at least if you try this, the processor should raise an exception, and the monitor should give him a chance to emulate the desired behavior. Also, all 7 instructions violate either part B or part C. That's about it's leaking information. So it basically just means it leaks information of the current processor state, which is not bad, but in specific it's bad because programs would like to use this information and would be misguided. So basically the x86 processor architecture is non-virtualization able. Bad news, but mainly my talk is about the x86 processor architecture today. So there are many ways where you can work around. So how to hack around these limitations. And there are plenty of possibilities. The first, change the hardware. of course. uh, Intel and recently AMD both thought this would be a good idea, like many other processor architectures have this already. I mean, this 17 instructions isn't something by design because it's sophisticated or complicated. They just didn't thought about it. Okay, if you can change the hardware, you can emulate the hardware. You can do dynamic recompilation of the code you are currently running or supposed to run. You can binary rewrite the code, also very dirty and often used in virtualization techniques. Of course, you can port the kernel, stuff like user mode Linux does this, or if you can't port the kernel or port the API because you don't have the source, you can try to emulate the API. There are some approaches using a microkernel, and last but not least, power virtualization and fractional kernel porting. So this is basically the techniques this talk is about. We are gonna talk about all of these techniques, how, I mean, yeah, all of these techniques. And but before we come to the funny and dirty part of it, we want to have another look at what virtualization monitor, or sometimes you call it hypervisor, depending on the implementation, should do for us. So first thing is protection management. Of course, it's important to seal the virtual and the physical architecture, and also important preventing virtual machines from interfering with each other or the monitor. Sounds reasonable. Of course, they don't have to know from each other. Another part of a machine monitor is resource management. I mean, giving a equal share of CPU, of network, of disk bandwidth. In case of CPU, network, and disk bandwidth, you just time multiplex. A space multiplex example is, of course, the memory. You need some paging support because probably the operating system wants to page non-used application memory out of memory. So you should support this too. Of course, virtualization gives us some things nearly for free. You can save a state of a currently running machine. You can recover the state at any other time, and you can migrate it to other machines. This is something that comes for free if you do virtualization. This is quite good. And of course, near to native speed. As I was looking through some implementation papers of virtualization on the x86, I discovered that all virtualization guys are Quake players. So it has to be near native speed. Well, to reach near native speed, machine monitor should at least, I mean, this is just a trailer, something like you need at least fast monitor calls. Means if something happens, you want to access the hardware from a virtual machine, you call the hypervisor. This happens quite often, so you need fast calls there. Also, you need fast interrupt handling. Every operating system has some idle instructions. You need to support this also. And of course, chunk writes for I/O would be quite satisfying in case you need near to native speed. Coming back to the Quake playing, this is from Denali, from a technical implementation PDF from Denali, one virtual machine monitor from the Forex 86. And you see, they already measured how many virtual machines of Quake 2, in this case servers, and the throughput they have. Well, 3 years later, there was Quake 3, and this is another virtualization monitor. This is Xen, and of course, the Xen guys are always doing the same. They are also looking if they migrate a Quake 3 server in while running, how long would be the downtime, and would this be acceptable for a Quake player? I think 50 milliseconds would be quite good. So virtualization helps playing Quake. Okay, but let's have a look at the techniques. First technique is, okay, the hardware change. Some people have made their thoughts about it. So the possibilities are just to change the 17 privileged instruction to trap into user mode and change a little bit of the semantics. Well, would be good because would be easy to implement if used as a switchable extension, also safe with legacy software. The bad thing about it is it's easy to implement. So, well, I don't know if somebody has tried, but I don't think you can make a patent on bug fixes. So, of course, you invent a new set of instructions and a new mode, and then you can make your new patent. So, basically, it would be sufficient to fix these 17 instructions and everything would be all right. But in case of reality, we need something different. Intel VTX and AMD Pacifica, probably for those who don't know, are extensions of the x86 architecture to work around the limitations of the x86 architecture. And if you have a look at the design papers, I had a look at it, it's quite terrific and complicated. But of course, it does what it should do. So Intel is shipping their new processors with this feature already, mainly in the server CPUs, but would take 1 or 2 years, and I think it would be mainstream. Okay, but we don't want to wait 2 years. So what else can we do? If we have a look at full emulation, full emulation has its good side and its bad side. Usually the bad side of full emulation is it's slow. The good side, you can run whatever box on whatever box, means you can run your Amiga operating system, you can run Windows on top of Linux, it doesn't matter. You virtualize every single piece of hardware, And as you see here, you're fetching some instructions, you translate them, and you execute every single opcode after thinking, what should I do with it? And then you update the virtual machine. It definitely has its good points. Box is one example of full emulation, virtualization. Of course, you have very good debugging capabilities for this. The other thing is you need to write a lot of code, because you need to write a BIOS, you need to write every single I/O device you want to support. But of course, Box is open source, and thanks to Box, many hybrid techniques of virtualization are only usable because Box has made the beginning and wrote many I/O and BIOS stuff. We will see this stuff in many other products. So full emulation is always a good thing if you want to try out something, but it's slow. Dynamic scan before execute, binary rewriting. Yeah, yeah. If you look at the slide, there's something I want to tell you. Don't try to use LaTeX Beamer to make very graphical slides. You fail. So basically, that's what I try to do. But now let's have a look at binary rewriting. Binary rewriting is a funny technique, because you write into the code while it's running. I mean, that's fantastic, yeah? It's not like database programming or real-time programming, where you do something very precise. Now, here you do dirty tricks and dirty changing opcodes while the system is running. Actually, you work around the 17 instructions again. But to work around the 17 instructions, first you must find them. Once you've found them, you put a breakpoint exception into it. This is just a 1 byte opcode, so that's quite easy. If you trap there, you know, okay, I'm here. That should be, I remember that should be that instruction. So I emulate these instructions and jump back. But you also have to take care about branches. So you must walk, of course, while it's running. I mean, while it is running in parts of it. Walk through the instruction opcodes, look for branches, mark these branches. If the code jumps into the other side of the branch, okay, you have to rewrite and look again what has happened. Do I need to examine another code segment, or is it just as we expected? So basically you do don't even think about self-modifying code. It's terrible with binary rewriting. But binary rewriting was one of the first techniques used in commercial virtualization. For instance, VMware does this in one part of its products, and yeah, as we see, it's working. I mean, it's quite fast, but we are far from native speed, and it's really dirty. So we want to do something different. Dynamic recompilation. Like binary rewriting, but a little bit more tricky. So dynamic recompilation is you pass one opcode, you behave again like the processor, but this time you don't rewrite it or do something, because it could be possible and different architecture. You pass it, you know the instruction, you recode the instruction into small C instructions, and while you keep care about the virtualized infrastructure, and then you translate these C instructions again into native machine code. So this is really funny, and because it happens to be quite fast, it's possible to support a different architecture than the host OS. You need only user mode support, so there's no kernel module you must load, and it's simple functions. Probably you know QEMU. Yeah, QEMU is one example for dynamic recompilation. And if you look at the progress of QEMU, you see it's working, and it's quite fast in incorporating new processor architectures. So, and basically it's a one-person project. So this is a technique used, which is really impressive in its results. Yeah, the bad things on this side is, okay, it's a little bit delicate, at least. I mean, it's not very dirty, okay? And also, again, you need to some way support self-modifying code, but it works. Yeah, sometimes you don't want to make a virtualization, a whole virtualization machine. You just want a API emulation. Everybody should know about Wine, I think. Does everybody know about Wine? Oh, okay. Wine is API emulation of the Windows API running on top of Linux. So basically that means API emulation is you have your Windows binary, and of course you want to run it on top of Linux or on top of FreeBSD. Insert your favorite open source operating system here. And to run this Windows binary, well, of course you need Windows, but you don't have Windows. So you need at least the function calls Windows supports. So, and this is where API emulation begins. You have, of course, beside of the loader and some relocation and other small support stuff, you have, yeah, all function calls usually used in Windows mapped to a library, which then calls x11 Linux operating system calls. So this is quite good, and for those who have already tried this, sometimes, well, it depends on the application, but right now there are many applications working. and many others don't work. Why? Because I mean it's quite fast, and also it's user space, so you don't need something like a kernel module. But as the Windows binary is expecting exactly the same trash for what it was built, it expects the same bugs also. So in case you have the source, this is not complicated, but in case you don't, it gets really, really, really hard. So you need to emulate every bug found in the system you want to emulate. In case of Windows, maybe you know that there are plenty of bugs. You need to be compatible with any of them. So also you need to emulate a lot of libraries, and this makes API emulation quite a hassle. You know, but if the program you want to use already works, use it. The bad thing on the other side is, well, it's hard to secure, especially if we are doing OS emulation. I want to, as I've mentioned before, user mode Linux falls in the field of OS emulations. That means you're basically taking the Linux kernel. I mean, user mode Linux is already integrated into the kernel, and wrap around the hardware, and instead of writing to real hardware, you are just writing to a Linux kernel. So you need to remap the hardware access to functions, and all the OS calls the applications want to call must be remapped to the real OS. This is quite hard to secure, and probably for speed you need a kernel module. But user mode Linux is working, and it has its field of application. But we have other approaches also. Well, this is maybe not wide known as an approach for virtualization. I mean, microkernels are, of course, well known to plenty of you. But VMware used this approach, and I think it's VMware ESX or GSX. Always swap these two. I think it's ESX, I mean enterprise something. And in VMware ESX they did something different. The guys from Xen tried it also, they failed. Well, I mean, it's a good approach to take a microkernel which has a built-in possibility to rewrite operating system calls from one flavor to another. I mean, you need at least for every operating system flavor call, you need a management API. But basically, it's good and it's easy. So you have here. It's probably a little bit unclear, but in this case, you have at least two translation APIs, one translating from Linux syscalls to the microkernel, and one translating from Windows syscalls to the microkernel. Well, it's a very clean implementation, and it's fast. But why did the open source project fail in this implementation? You need lots of code. especially you need every device driver. You know, probably if you have looked at the kernel code of Linux, you will see that most of the code lines are drivers of devices. So basically, and hardware is changing fast. So, I mean, at FireWeb somehow they did manage to make it, but there is no open source implementation of this because you need to write a lot of device driver, and after half a year you need to write new ones. So let's come to power virtualization. Power virtualization, the most prominent example of this is Xen, is making a little bit of different approach. If we can't virtualize the hardware because of some minor bugs into the hardware, okay, we work around these minor bugs not in emulating it, not in binary rewriting it. No, we change the operating system, just in small pieces. So basically we want an ideal hardware where every single access to the hardware is going to a management API in the monitor, in the virtual machine monitor. And we don't want to write drivers, so we're using the host OS to pipe the drivers to guest OS, the data to guest OS, and we just need a thin, very thin layer of virtualization between the real hardware, because we modified the operating system not to call the hardware direct, because we want to call the machine monitor instead. So the good thing, this is, if implemented right, this is very fast. Also, it's capable, scalable. Mean you have a linear overhead, and the hardware support, of course, is easy. You're using your host OS for it. On the bad side, you need a modified kernel, and means you won't. There was in the lab there was a Windows version they modified, and didn't take so long. But in reality, Microsoft or commercial operating systems have no real fun about running on top of open source operating system. So that won't happen, even if it's not complicated. And comparing to the microkernel approach, probably forgot in the last slide, there is also one difference on the bad side. In the microkernel approach, of course, you have your device drivers, you're doing all the stuff by yourself. Here, if the host or one hardware domain crashes, well, every other domain which needs data from this hardware domain is also halted. And this was what's coming up next in the next few months. I mean, it's already running, but you don't get a hardware for it. You can, of course, combine power virtualization with virtualization as soon as the hardware gets better. There are a few differences between the power virtualization, full virtualization, and full virtualization. Of course, need something like a BIOS, and of course you need some I/O emulated. even if you don't use it all over the time, because there are device drivers where you can pipe it through the machine monitor to a hardware domain. You want to boot unmodified OS, so you need a lot of things. Well, Box, again, did many of this code because of the BIOS, and QEMU did a lot of I/O emulation. So what the XAMPP people thought was, well, let's put the new hardware change, the BIOS of Box, and the I/O emulation of QEMU together, and of course Xen. And basically then you have full virtualization with linear overhead and near native speed. 10 minutes. Probably I will skip that one. You see here's a short overview. It actually scales. So what we have seen today on different types of virtualization techniques is emulation, box, dynamic recompilation, QEMU, kernel porting, API emulation, power virtualization, and full virtualization. And of course there are always some kind of hybrid techniques. But you see virtualization on the x868 platform. I think it's day 4. I really feel it. There are a lot of products, and there are lots of working products, and most of them are open source. So what should we do with it? So let's have a look at the future. If everything is evolving in the way it looks, in my opinion, soon a virtualization monitor will become part of a standard bootloader. So maybe it would not be the standard bootloader of Windows, or maybe not the standard bootloader of macOS, but at some stage it will be a standard bootloader, meaning you have always virtualization on board, if you need it or not, but if you want to start a virtual machine, whatever you run on top of it, you will be able to. A little bit more advanced, but not so far in the future. Linux, BSD, and ReactOS. ReactOS, for you don't probably. ReactOS is Windows NT kernel clone, which is progressing quite good. I mean, it's not finished, as most open source products or any other product, but it can run already a couple of applications. And the interesting point in this case, it's of course very easy to port it to run under the Xen hypervisor. And interesting thing, it can run Windows drivers. So what do you want to do with your laptop wireless card? Well, most of the time you choose to run Windows because there is no driver for it under Linux. Yeah, in the upcoming future, there is no need for Windows, Linux, or whatever, if there is a driver in either Windows or in Linux or in FreeBSD, you use it as a hardware domain and put multiple hardware domains, each having a specific piece of hardware under control together, and run it probably a third or fourth operating system where you will be doing your real work. So the NAOS is, in my opinion, just incorporate every operating system you want. It will run under the virtual machine monitor, and you can use the drivers of every operating system, because you have every operating system running on top of your machine. And also in the future, I would say, whenever needed, virtualization will become a key technology in privacy enforcement. I mean, probably everybody of you know about the Sony case. And, imagine a future, a not so far away future, where the digital right management chain is closed, meaning you have a TPM chip which is under control of the BIOS. You boot a certified operating system and you're using certified drivers, and of course this is the precursor to use your certified Blu-ray disc player and to play back your high definition television or whatever media. You need to have that certified chain of digital right management, and of course your graphic cards will have an HD and a digital output with content protection. So basically you're screwed. Yeah? And there is no easy way to work around it, because either you circumvent the encryption, which is illegal, or you circumvent different other things, which is also illegal, or, well, you could virtualize the whole machine, and at the end you're writing in a virtual frame buffer, and well, in a different operating system which is running beside, you do whatever you want with it, and it's not inflicting some digital right management copyrights. You're not doing some bad breaking of cryptography of right management, and of course the operating system has no idea what is going on, and so has the digital right management. So in the future, probably, hopefully, in a very past future, or hopefully you don't need it, but full virtualization is probably the key technology you can use in a dark future where the digital right management chain is closed and you have no way to escape it except of virtualizing it. So well, I think this was it on my part. For people who are interested in the deeper techniques, I have some references in my slides. You can download the slides, of course, from the wiki. And yeah, questions? Yeah. Okay.